Hello everyone and welcome to this lecture on modeling in bioprocess engineering. This lecture is gonna be split into three screencast videos where we're gonna work through first the basic principles of modeling in bioprocess engineering. In the second part, we're gonna focus on modeling in chromatography. And in the third part, I'm gonna give a short introduction into Cadet, free open source software that we are using for our chromatography modeling. We're gonna start our lecture today by asking some questions that we want to answer during the lecture today. These are: why are we actually building models and what makes a model useful? We have some more questions. Why do we build models? What kind of model exists? And why are mechanistic models used in downstream processing? These are all questions that we are trying to answer today. Short graphical abstract of what we are going to be talking about today. We want to have real processes, transform them into models to then predict, optimize, or control our systems. Okay, why do we build models? The first most important takeaway is that a model is always built because we want to answer a product-related questions. These questions could be different. They could be understanding. So we want to better understand the process. Why does a process behave in a certain way? Why is thing X happening at time point Y? A second big point that is always a big point in industry especially is that we want to have to perform fewer experiments. We want to have a model that is taking the load of experiments from our shoulders. Experiments are expensive, they are time consuming, so having a good model can help us reduce trial and error. So we have to do less experiments. A model maybe even allows us to do more digital experiments in a shorter time for a lower cost. We might want to use models as a predicting tool. So we have maybe already a process, but we want to know what happens if we change anything about the process without having to do the experiments. This is where prediction comes into play. That may be the most obvious reason to have models is to use them for optimization, right? Complex problems like, let's say, chromatography have many input parameters, many factors that you can fine tune, and models might help us to improve some parameters like yield, purity, or the productiveness generally of our process. And the last point that is a really fast growing and even or each year more important point, especially for industry, is control. Models are often needed for online monitoring systems. They are needed in advanced control schemes and also for digital twins. So important takeaway is that the model is never built just to build a model. The model is always built with a purpose, with a clear goal in mind of what we want to solve with our model. Then a big thing to clear up is what is actually model. We're going to be talking about models a lot. When we talk about models, we mean a system that is a simplified representation of a real system. This model or this simplified representation has inputs. So these are parameters or important information that enters or affects the system. This could be like the concentration of like a target molecule. This could be the temperature of our process. And then we have the model that is doing the actual modeling. And this model is made up of states, parameters, and assumptions. And here I want to especially point out assumptions. Assumptions are simplifications that we make when building our model to simplify the real process and to neglect what is not important or what we think does not have an impact. And then at the end, we have the outputs. These are the parameters or the results that we want to observe or that we want to predict. So all models are a simplification of the reality, but if you have a really good model, it simplifies reality in a useful way. This is already a good connection to model complexity, and model complexity is a trade-off. This means a simpler model, right? A simpler model that has maybe more assumptions made, has an easier application. It has a lower demand on data for calibration and validation, and is also faster in computing, which is an important factor, especially when thinking about doing a lot of simulations. On the other hand, more detailed models, they normally require a higher computational effort, they need more data, and most of the time they're also made up of more parameters. The upside of the more detailed model obviously being that maybe the model can catch some effects of the real system better. Maybe the simple model is just not enough in representing a complex system. I want to have said that all these things are usually applying. However, sometimes you cannot generalize how models work. And the takeaway from this slide is going to be that the best model is not the most complex model, but it's the model that is the most appropriate for your application. To answer the next big question of what main types of model exist, we're going to look at the three main classes of models. There are obviously many more subclasses, but these three cover most of the subclasses. So we have first so-called empirical, or also called black box models. They're called black box because we don't really know what's happening inside. We can only look at it from the outside. We can input stuff into the model and we can then get the outputs. However, they have limited physical meaning. What do I mean by this? Maybe let's give a good example. Let's say we want to build a model that can predict the price of a house from three given parameters: location, size, and the age. So to train such a black box model, it could be a machine learning model, it could be a Bayesian model. To train these black box model, we need a large data set. We can maybe get this from an online real estate platform. And then the model learns on the data, learns the relationship between these inputs parameters and the output parameters. And after the training is complete, we can predict the price of any new house from our three parameters: size, location, and age. However, the model cannot give us any information on how this reasoning, or what the reasoning behind the price is, right? So you cannot ask the models things like, okay, if I increase what is the most important parameter, size, location, age, the model will not be able to tell you. And also thinking about working out of our range, if we have calibrated this model, let's say in one city, this model will probably not fit in another city where some different outside parameters that we have not taken into account might be different, right? So this black box model is only ever as good as the data set it is trained on. Second, we have mechanistic models, also called white box models. This is the complete opposite. So here, this model is based on physical and chemical principles, which also means that the results are physically interpretable. The easiest example for this might be any mechanistic equation. Let's say you want to describe the speed or the distance that a falling object is traveling using the equations of motion. You have probably already done this in your studies at some point, and because this model is derived of these laws, this model is interpretable, but it's also transferable, right? So you could use this motion model, let's say, on the moon. You have to adjust some parameters like the gravitational pull. However, the model is still sound at a different place from where it was built, so it can extrapolate outside of its calibration range. And then last of the three bit groups are the hybrid models, also called gray box models, um, originating from mixing a black box and a white box model. You get a gray box model, and that's also the idea. These combine both ideas. They combine mechanistic structures with some data-driven elements. And a good example here might be a model that can predict how a room heats up. You can describe this using some simple energy balances given the output of your heater and the volume of the room. However, things like the heat loss through the walls are quite complicated. The walls might have different geometry, might be built of different materials. So we could try to approach the heat loss part of our model with a data-driven solution, while the volume and the heat input are derived from a model-based system. So this is how we can have these combined hybrid gray box models. There are some additional ways that you can use to classify models. If you're talking about the dimension of time, a model can be static or dynamic. In static models, there is no dimension of time. So these are models that are not interpreting processes that run over time, but look at a fixed time point, while dynamic models take time into account and describe how a system changes over time. We can then also look at lumped versus distributed models. Lumped models normally ignore a spatial variation, whereas the distributed models take into account the dimension of room. Also, they resolve the model across space. And then lastly, we can also differentiate models between being deterministic or stochastic. Deterministic models will always give you the same result if you have the same inputs, whereas the stochastic models make explicit or explicitly include some randomness in their process. At this point, you can maybe already stop the screencast shortly and think about what types of models are probably going to be used in chromatography. Are they static dynamic, lump distributed, and so on. I want to also give a short overview over how modeling is used in bioprocess engineering and where it appears. And the simple answer is it appears everywhere in bioprocess engineering. Um, the models appear throughout the entire bioprocess, but they differ in purpose and they depend on what stage, what they are used for. So maybe if we start in cell culture, we want to maybe get an estimate of our cell growth, how our substrate is consumed, and how the product is formed, right? And for this, we are using kinetic growth models, we are using material balances, we are using models for biomass. So here we maybe want to optimize our growth, right? We don't want to put in too much substrate, but we also want to have enough substrate. So this is where models come into account, maybe um, for online monitoring and real-time control. Looking at the next step, typical step, the bioreactor. Here we have mixing effect, we have oxygen transfer, the pH and the temperature are to control and measured. Here we have then models for the oxygen transfer, again mass and energy balances, but also maybe for the mixing fluidic simulations, right? Looking into the next step where we go into harvest and filtration. Filtration, here we maybe want to model the flux of our system. We want to get a model that helps us understand fouling better of our membranes, maybe a model that can predict what is the lifetime of our membrane. And here we can take into account often black box models that look at fouling or resistance in series models. And then lastly, when looking at the purification steps of downstream, mostly chromatography, we want to look at parameters like the elution, the yield and the purity, but also the productivity. And here we have as we are gonna see later, we're gonna look into absorption models and generate models. So as you can see throughout the whole bioprocess process, we are having different models that apply for different purposes. So to transfer from this basic introduction to modeling into chromatography, let's look at what is happening in chromatography. And chromatography, as a start, is a coupled transport and binding problem that combines several effects. You might have maybe seen a scheme like this already. You can see a chromatography column, and then we zoom into what is happening inside of our liquid and stationary phase, and then we zoom once further into the stationary phase, and then zoom a third time onto the surface of our adsorbent. So this chromatography model that we're going to look at later is going to combine all these effects. It's going to combine the fluid flow through our column, so the convection. It's going to look at dispersion, so the movement of these molecules inside the fluid phase of our column. We're going to look at mass transfer, so the transfer of molecules from the liquid phase inside of the pores. And then we're going to look at the transport inside the pores, so the movement of the molecules inside of the pores themselves. We're going to look at absorption, desorption effects on the surface of our molecules, and then we're also going to look at surface movement. So as you can already imagine, these models are quite complex, so they don't look at one singular effect, but they combine multiple effects. To summarize this basic introduction into modeling, I want to recapture some of the most important parameters. First, that models are a simplified but a purposeful representation of a real system. That models are always built for one of these goals, either understanding, prediction, optimization, or control. Every model that we are building is based on assumptions that define the strengths and the limitations of a model, and this is quite important to know the limitations of your models. What is your model good for? What is your model calibrated for? What can your model do and what can your model not do? Model selection, we have discussed what different types of models exist, and the selection of really depends on the application that you want to use your model for, what data is available, and how complex your model needs to be. Mechanistic models are always especially useful if you want to also be able to have interpretation and extrapolation. So if you want to use the model for a better understanding of a process and also maybe want to use the model to predict something outside of the calibration range, then you're going to have to go back to mechanistic models. Also, that simpler models are most of the time easier to use, while detailed models obviously can provide a deeper physical insight. We've also learned that in bioprocess engineering, different unit operations require different modeling approaches, and that the purpose of the models changes along the process chain. In downstream processes, we are often using mechanistic modeling. This is because most of these systems are quite well described. You have physical parameters. You have physical parameters that you also want to control in your systems, which is why we're going back to mechanistic models. Chromatography, as we're going to be seeing in the second screencast even more, is understood as a coupled transport and binding system. And because these mechanisms are physically meaningful, so the transport through the column, the binding to the surface, we are using mechanistic models for our chromatography modeling. So thank you for your attention to listening to this screencast, and I hope I see you again in the next screencast where we're going to especially talk about modeling in chromatography.